Okay, so moving on to chapter 4, question 37 is asking you to give the major product of each of the following reactions. So overall, both of these reactions, actually all four sub-questions, are dealing with very simple addition reactions, and there are a couple of constants that'll remain for all of these questions. The first is your alkene. So you're going to have an alkene for all of these reactions. That's going to be constant. The second thing to keep in mind is that they're asking you to talk about the major product. So basically they're asking you about regiochemistry, about which carbon is going to house a hydrogen and which carbon is going to end up housing a bromine for all of these. And so because of that fact, you are going to have to rely on your knowledge about Markovnikov versus anti-Markovnikov regiochemistry to talk about the products from these. Okay, so what I'm going to do is I'm going to go through each and talk about how the general rule for Markovnikov works, and from there go into the mechanism for why it works. Because sometimes just knowing Markovnikov isn't sufficient, because sometimes some funky things can happen with the intermediates that give you products that you wouldn't expect just if you applied the generic Markovnikov rule. Okay, so it's always best for these problems to think about the mechanism, and because they're really, really important for rearrangements that we'll talk about later on. Okay, so first off, we have this alkene and this HBr acid. The first step for all of these is you need to determine which molecule is the nucleophile and which molecule is the electrophile. For all of these, the nucleophile is actually pretty simple in that the alkene is always going to act as your nucleophile. So again, when we talk about nucleophile versus electrophile, the nucleophile is going to have a high density of electrons around it to give, and the electrophile is going to have a deficiency in electrons. So first step is to recognize the nucleophilic molecule, which is this guy, this alkene. And the second step is to figure out what's going to be the electrophile, and that's going to be our HBr. Okay, so that part's pretty simple. So for this problem B, it'll be the exact same thing. We'll have our nucleophile down here, our electrophile right here. And so then after that, you have to zoom in and actually figure out what part of the molecule is actually acting in a nucleophilic way, and what part of the molecule might be acting in an electrophilic way. So the nucleophilic portion for the alkene is always going to originate from the double bond. The double bond has an excess of electrons, and they are housed in the pi bond, so this second bond right here. So this is going to be the nucleophilic portion. For the HBr, it may or may not be obvious which part is the electrophilic bit. So this actually boils down to thinking about electronegativity. So the electronegativity is going to be as such. So you have our H and our bromine. So the bromine is going to be way more electronegative than the hydrogen. So if you drew your electronegative arrow, this is going to tell you that your partial positive charge is going to reside on your hydrogen, and your partial negative is going to reside on your bromine. Same thing here. So partial positive on the H, partial negative on the bromine. So now that we've recognized the electrophilic portion of the HBr, we have to show how electrons move from the nucleophile to the electrophile. And again, the electrophilic part of the HBr is the hydrogen because, remember, electrophile is saying electron loving. So electro is electron, phile is loving, so electron loving. So something's going to be electron loving if it is already electron deficient, which this H is. So that's because it has that partial positive charge. So let's go ahead and show electron movement from the alkene to the HBr. So again, electron movement is going to originate from the pi bond and it's going to end up on the hydrogen. So this is the way you would draw this. So you would show electrons starting at the pi, ending at the hydrogen. Okay. Sometimes I'll see this where electrons or students are trying to say that electrons are starting from the hydrogen and going to the double bond, which is totally impossible. I think most times people have the right idea in which they're trying to form a bond, but basically whenever you write this, what you're telling me is that hydrogen has electrons within the nucleus of the hydrogen. and or the hydrogen has a lone pair, which is obviously incorrect because if that was the case, hydrogen would be breaking the duet rule. So hydrogen never, ever, ever has a lone pair. So that's right out. And so because of that, arrows can never be drawn this way. Arrows can never be drawn where the origination point starts on the hydrogen and the wherever they're going ends up on the double bond. Okay, so this is totally wrong. So you'll never draw it like this. Okay, so again, we'll always start on the pi and end on the hydrogen. Okay, so start and end. So now, for the same reason we couldn't draw a lone pair on the hydrogen before, we cannot just leave this electron pushing like it is. So if we make a bond, we actually have to break a bond. So between the hydrogen and the bromine, we're going to remove that bond and show all the electrons going to bromine. Okay, so now at this point, let's go back to the Markovnikov versus anti-Markovnikov bit. So this is basically being talked about because this initial electron movement is very ambiguous about where you're going to end up putting this this hydrogen right here, this orange hydrogen. Right now, according to the way that this arrow is drawn, the hydrogen can either be placed on this carbon, carbon A, or this carbon, carbon B. And so the way that you figure this out is you have to actually go through both possibilities if you're going to go through the mechanism. But for now, let's just go through this problem via Markovnikov's rule and see what we get and see why we actually get that. So according to Markovnikov's rule, we're going to put this orange hydrogen on the atom that already has the most number of hydrogens on it. Okay, so first thing you have to be able to recognize is that carbon A actually already has a hydrogen. This is an implicit hydrogen. It's not always drawn. It's not lacking this hydrogen because otherwise this carbon A would have only 1, 2, 3 bonds, which would mean it would have to be positive. And because the question is framed in that carbon was neutral, or it's drawn neutral, you have to assume that there's an implicit hydrogen there. Okay, so now, according to Markovnikov, we're going to want to put that orange hydrogen on carbon A because it already has 1 hydrogen, whereas carbon B has 0 hydrogens. So because we'll put this orange hydrogen on A, we're going to end up putting the bromine on B. So I'm just going to go ahead and draw 2 little arrows to indicate that we're just skipping ahead to show the final product. And I will put this bromine, I'll just leave it white. Okay, so our final product is going to look something like this, where we have 1, 2, bromine here, and we'll have our beige or orange hydrogen coming out here, and this was our original hydrogen right here. Okay, so according to Markovnikov's rule, this is what we should get for this addition reaction as the major product. And indeed, this is actually the correct answer, so that's great. So it's a really simple rule, but sometimes it's going to fail you. So it's not sufficient for you to just know this rule. You need to go through the mechanism every single time if you are worried about certain things such as rearrangements, which we'll talk about rearrangements a little bit later in class, and we'll probably have a couple of examples here. But in this case, we don't really have to worry about it too much, so we'll get the same answer either way. But anyway, later on, we'll see how rearrangements can muck up this whole Markovnikov rule thing. So anyway, let's actually go through the mechanism and see what will happen if we actually go through the mechanism. So going down below, going through the mechanism. So we'll redraw the cyclohexane right here. So at this point, we have broken this pi bond. We still have a hydrogen right here. Okay, and we still have this ethyl group right here. Okay, and at this point, basically, because of this ambiguous nature of this yellow arrow push, we have to go through 2 different possibilities of where to put that orange hydrogen. We can either put it on carbon A, or we can put it on carbon B. Okay, so we can either put it here or here. Okay, so this first possibility, let's just say we ended up putting that hydrogen on A for the first scenario, and then let's say, well, what if we put the hydrogen on carbon B for the second scenario? At this point, we have a bromine, negatively charged bromine, just kind of floating around in solution, so I'll draw it down here. So this should be a tip-off to you that something's amiss, because always, 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 you need to make sure you have charge balance. So right now, the overall charge balance on this equation is negatively charged. And if you look up here, the overall charge balance is neutral. So that means that we need to figure out where a positive charge is coming from. And because of the nature of the mechanism of this addition reaction, you should know by now that the intermediate is going to be a carbocation. Okay, so the carbocation in this case could go on one of two possible ways, or one of two possible positions. It can either go on carbon B, so we can either have a positive charge here, and we know that because carbon B only has 1, 2, 3 bonds, so if you do a valent or a formal charge calculation, you'll see that carbon B should have a positive charge. Or that positive charge can go on carbon A, because again, carbon B has 4 formal bonds, which is great. That gives a neutral carbon. And carbon A, again, in this case, only has 3 bonds. So the second scenario would be where this carbon A has the positive charge. So at this point, you have two different possibilities. And at this point, you should be able to figure out the class of carbocation that we have. And so in this case, we actually have two different types of carbocation possibilities. This one on the left is going to be a tertiary carbocation, and the carbocation on the right is going to be a secondary carbocation. And in terms of stability, we've already said that tertiary carbocations are more stable than secondary carbocations, which then in turn are more stable than primary, which in then turn are more stable than methyl. Okay, so because these tertiaries are more stable, we're going to have the molecule choosing to go through this lower energy pathway to form this lower energy product. It's more stable. So the first thing you need to realize, or the second thing you need to realize now, is that because this tertiary is going to be way more stable, secondary isn't even going to form. Okay? And so because secondary isn't even going to form, we can now hone in and focus on this tertiary carbocation. Okay, so now we have our carbocation. The carbocation is now electrophilic for the same reason that this hydrogen was electrophilic to begin with. And now the bromine is nucleophilic for the same reason that the pi bond here was nucleophilic to begin with. Okay? An excess of electrons here, a deficit of electrons here. And so we already know that we're going to end up having the bromine add. And the easiest way to do that is by just drawing this singular arrow right here. And in this case, we actually don't have to follow this mantra of making a bond and breaking a bond. If we make a bond, we break a bond, because we will not be violating any octet rule. So in this case, we can get by with just making a bond, and we don't have to worry about breaking a bond anymore. Okay, so now that we've done that, we can show our final product, and it's going to look like this. So we're going to have our cyclohexane, and we're going to have our ethyl group, and we're going to have our bromine attached right here. Okay, so if you look at this initial molecule that we drew versus this bottom molecule that we got to after going through the mechanism, they're the same molecule, which isn't too much of a surprise. It just took us a little bit longer to get there. And ideally, being able to predict the product via the top method versus the bottom method shouldn't really take any real difference in time. They should be about the same in terms of your efficiency. It was just a little bit longer to go through because I was trying to be really explicit in why we did every little step. But ideally, going from here to here via this pathway is just as fast as doing it this way. Okay, so overall, this is still operating via a Markovnikov pathway, and nothing funky is going on really. So, but later on, we'll get some rearrangements which will make things more interesting. Okay, so let's go through the second sub-question B. And I'm just going to go through this very quickly, going through the mechanism, and then I'll show why we still get a Markovnikov product. So if this was just me doing this, I would say double bond, nucleophile, HBr, electrophile. Going to make a bond, break a bond, and so after that, we'll redraw our guy. We no longer have an alkene, we now have an alkane. We're going to put the positive charge here because we're going to form a tertiary carbocation, which is going to be more stable than a secondary carbocation. We're going to have our Br minus in solution, nucleophile, electrophile. We're going to draw our newly formed bromine carbon bond, and we're going to get our products. And that's it. So that took about 15 seconds, maybe, at the most. And again, in this case, we're getting a Markovnikov product, okay? Because what we ended up doing was we put this hydrogen on the carbon that had already the most number of hydrogens. So again, this is carbon A, this is carbon B. Carbon A has 2 hydrogens, and now what we're doing is we're adding a hydrogen, or the orange hydrogen, to that. So here we have 2 hydrogens right here, 2 hydrogens right here, and we ended up adding the orange hydrogen to carbon A because it already had the most number of hydrogens. Okay, and this is our final product. This is the Markovnikov product, and this is completely correct answer. This will get you 100% total credit on an exam. Okay, all right, that's it for that one. And next question.